Hello students, as we have studied about the composition of the nucleus till now, so now we are moving to its size and density. So first talk about nuclear size. Just like an atom, nucleus is also not a solid object, right? It doesn't have a definite, well defined boundary, but we can assign a size to it depending on the order of its radius. So we basically define the order of the radius that nucleus possess, and to get that answer, to get that order, we perform scattering experiment using high energy probes such like fast moving protons, neutrons or electrons. And by using these high energy probes, we can find nuclear sizes of different elements experimentally. So basically we are going to find the size of a nucleus, the radius of a nucleus experimentally. So experimental observations that were performed, it gives us a result that the volume of a nucleus is directly proportional to its mass number. That means if we have a nucleus of a large mass number, its volume will be large. So the experimental result that we are using, the fact that we are using is the volume of a nucleus is directly proportional to the mass number, and we assume that the nucleus is of spherical in shape. If the nucleus is spherical with radius r, so if we have a nucleus which is spherical in shape and has a radius capital R, then we can give its volume as 4 upon 3 pi r cube, and this is proportional to the mass number capital A. Now 4 upon 3 and pi are constant, so this proportionality shows that r cube is directly proportional to A, or r is proportional to A to the power 1 by 3, right? Hence, using this proportionality, we can define the radius of a nucleus as proportional to the cube root of its mass number, or we can give it as r is equal to r naught A to the power 1 by 3, where r is the radius of the nucleus and r naught is a constant. This r naught is a constant, and this r naught is of the order of range of nuclear force. So this constant is of the order of range of nuclear force, and it is equal to 1.2 into 10 to the power minus 15 meter, or we can write it as 1.2 Fermi. So it also act as a unit to measure the nuclear size, or we also call it as nuclear unit radius. Okay, we also call it as nuclear unit radius, and it refers to the average nucleon size. Average size is represented by the distance r naught. It is equal to 1.2 Fermi, and we can give the value of radius of every nuclei in terms of r naught. For example, if we have a nucleus of mass number 4, then its answer will be r is equal to 4 cube root 4 r naught. So that's how we can give the nuclear size of any nucleus. After nuclear size, the next thing that we have is nuclear density. So nuclear density is the ratio of mass of a nucleus to its volume. As the density is mass upon volume, so nuclear density is ratio of mass of a nucleus to its volume. Let's find the nuclear density for a nucleus with mass number A and the radius r. So if we have a nucleus with mass number A and radius r, these two quantities we know, and we want to find the nuclear density of that nucleus. So if we are assuming that m is the average mass of a nucleon. M is the average mass of a nucleon. Since mass of proton and mass of neutron is slightly different, so we consider that m is the average mass of a nucleon, whether it is a proton or a neutron. So in that case, the total mass the nucleus possesses is mass of nucleus is equal to a number of nucleons in that nucleus is A, and every nucleus has an average mass of m, so total mass is ma. This is the mass of nucleus. Now volume of nucleus is, if we assume nucleus as a sphere, then the volume of nucleus is 4 upon 3 pi r cube, and for r we can substitute the value r naught a to the power 1 by 3 ka cube. That means this volume of nucleus is equal to 4 upon 3 pi r naught cube a. Now if we take the ratio of these two factors, we get the density of nucleus. So density of nucleus is represented by rho. In suffix we have written nu, which represent that it is the density of nucleus. So this is equal to mass upon volume. Mass is ma and volume is 4 upon 3 pi r naught cube a. If we solve this, we get 3m upon 4 pi r naught cube. So this is the required answer, required density of nucleus. Now we can clearly see here that rho is independent of the mass number. Rho is independent of the mass number a. There is no a present in the relation. Also it is also independent of the radius r. So basically the density of nuclear matter is independent of the size of the nucleus. The answer that we are getting here has all the constants, so we know the value of m, which is the average mass of the nucleons. We can put it as 1.67 into 10 to the power minus 27 kilograms, and the value for r naught is 1.2 into 10 to the power minus 15 meters. If we substitute these two values along with the value of pi here, we get the density of nucleus is equal to 2.3 into 10 to the power 17 kilogram per meter cube. So this is the required answer for the nuclear mass density. That means the nuclear mass density is of the order of 10 to the power 17 kilogram per meter cube, which is very large as compared to the density of ordinary matter. Right? For ordinary matter, the density is approximately 10 to the power 3, 10 to the power 4 kilogram per meter cube, and in case of nucleus, if we talk about the nucleus only, it is 10 to the power 17 kilogram per meter cube. This shows that the packing of nucleus is quite tight. There are so many nucleons in a very small space inside the nucleus. They are closely packed. This is shown by the density of the nucleus. So that's all about the video. For further videos, stay tuned and keep studying. Thank you.